All right, so let's look at some examples that involve population models. All right, so these are uh, differential equations that are meant to describe the growth of populations. We kind of threw one of these at you early on as an example of differential equations, but let's just take a little look at them a little closer. So the first one we're going to just look at real quickly is just the general population model. Let's do this. Right, we're just trying to describe we're trying to describe the population of people in a country or in a city or animals on an island or bacteria in a dish. Just trying to come up with an equation that describes these populations. All right, so the general population model is simply this, and P is capital P is the population function. So the general population model looks like this, that the change in population, dP dt, is equal to the difference between the birth rate and the death rate, so beta and delta, times P. Okay, now beta and delta could be constants or they could be other functions of t. But that's just generally the general population model. We're not dealing with, we're assuming unlimited resources and space and size, but that's our differential equation. All right, and of course we are trying to solve that for p, for the function p, so that we have a formula that gives us the population at any given time. So if we look real quickly at this this problem right here, where we say, okay, we've got alligators. All right, and they start off with the initial population. Let's spell that correctly. So initial population equals 100. Okay, so that means P times 0 is 100. So there's our initial condition. All right. Let's say the death rate is 0. So they're not dying off. But the birth rate, all right, the birth rate, beta, is equal to 0.0005 P. So that birth rate is getting bigger as the population grows. All right. So if we know those things, then we know what our model is for this population, right? It's the birth rate minus the death rate times P, or simply 0.0005 P squared. And if we can solve that, then if we can solve that for P, then we have a model describing the population, right? So it's at this point, once you've established the model, then you just go into the solving mode. This one we can solve by separating variables, right? So we end up with dP over P squared. We'll do that. We'll do it that way. Equals 0.0005 t. Remember, t is the independent variable, so that's why I'm leaving the 0.0005 over there with the t instead of dragging it along with the p, because I want to make the p side as simple as possible. Okay, so the antiderivative, or the let's move it over here. So if I integrate both sides, right, we get -1 over p equals 0.005 sorry, and I back up just a moment. If I could edit this out, I would. That's not 0.005, it's just 0.005 back here, right? 0.005, and then we're differentiating that one with respect to t. So that leaves us 0.005 t plus c, okay, or p is equal to -1 over 0.0005 t plus c, right? And then I can go on to find what c is. Well, it turns out that c is, if I plug in 0, 100, I end up with c being -1 over 100, right? And so if I put that in there and clean everything up, I end up with this equation. P of t equals 2000 over 20 minus t. Okay, so there's my model, all right, for this population. So of course, once you solve it, that's one thing, but I've always found it a little bit helpful to go ahead and look at the graph of the slope field along with a few of the solution curves for different starting values, and that's what you see right. So I just graphed the slope field, and then some different solution curves for different initial values. Our curve is this bottom one. This bottom one is the actual solution to the initial value problem that we're dealing with. But you can see they all behave the same way. You can see that while they start at wherever they start, the population grows, and eventually it just starts growing. And in these other examples, you can really see it growing almost exponentially, not quite, but growing very, very quickly and without end. And that makes sense given that this is a population with a birth rate that is increasing but no death rate, right? So they never die. So we would expect the population to go to infinity regardless of where we started, right? And you can see that. I always like to look at those graphs to verify that things behave the way they should. All right, so that's just our general population model. Let's throw in here now one that maybe is a little bit more realistic, that maybe models real life a little bit more. And this is, we've seen this before, this is the logistic growth model, and this is a model where your birth rate is actually going to go down, okay, depending on how many people there are, how big your population is, which makes sense, right? If you're a bunch of rabbits living on an island, eventually you run out of food or space or whatever, and your birth rate goes down as your population grows. And these are the kind of situations where we deal with a limiting factor or some sort of carrying capacity. But they do start with the general population model, which, you know, as we said, looks like this. You've got your birth rate minus your death rate times p, right? And that's your general. It just so happens that our birth rate is variable. It's not constant, it's variable, and it is decreasing. All right, so we can add that in here. If the birth rate is, say, a linear decreasing function, so it looks like this, we've got some fancy notation here, but in the end that's a line, right? Mx plus b, and it's a decreasing line, right? Negative slope. So if that's your birth rate, then you end up with a differential equation that looks like this, where your birth rate is some constant minus some constant times your population. This is saying your birth rate is decreasing as the population grows, minus your death rate. And if we do just a little bit of algebra on that and maybe simplify our variables, or simplify the constants, we just end up with something times p minus something times p squared. and doing just a tiny bit more simplification, factoring out AP, or factoring out some portion of A, not totally AP, we get this right here, K times P, M minus P. And this is our logistic model. And the important thing is this value right here, M, is our carrying capacity. That's why it is structured that way, right? So if we know how many rabbits our island can support, then that value goes in there. All right. So let's just look at a real kind of simple one of these, because we need to review something that's kind of important here. So let's suppose we're just dealing with this right here. This is actually one that we dealt with. This is the example we dealt with before. Dealing with a population where the carrying capacity is 150, right? And so there is the differential equation, right? Now we can actually solve this by separating the variables. Okay, so what we'll do is, of course, we'll move. Let's do it this way. We'll move the p's over under the p, so we end up, or under the dp, so we end up with p times 150 minus p equals 0.0004 dt. Now that's easily separable, right? All we're going to do though is and we would differentiate this, right? All we're going to do is focus on this. And this is more of a integration review, okay? Because once you get to this point, you need to integrate, and you need to be able to integrate these things. So I want to just go over how you would integrate this. And the technique, and this is a technique you've learned but you maybe have forgotten, we're going to use partial fractions. So like I say, this is mostly just an integration review at this point, in order to get us to that point. So what we're going to do is we're going to take our expression, which is 1 over p, 150 minus p, and in partial fractions you want to break that kind of complicated and large rational expression up into a sum or difference of smaller rational expressions. And so what you do is you factor the denominator, and you do that first. And once you've done that, you know that you can break this, you can decompose this into something over p plus something over 150 minus p. And the way I always think about explaining why that's the case is, I imagine if I had these two fractions and I were wanting to add those together, I would need a common denominator. And what would that common denominator be? It would be this times this, or that right there. And so I would end up, if I added these two, I would end up with a fraction with this as the denominator. So if I decompose it, I can do the same thing. I can say, all right, well, this could be broken down into something over p plus something over 150 minus p. And it is our task at this point to figure out what these two somethings are. Right now, partial fractions can get more complicated, and it might be that you need to use more complicated techniques. But for this particular example, it's pretty straightforward, because now we need to figure out what a and b are. So our technique is this: multiply both sides by p times 150 minus p. This is just a simple algebra right here for us. And that, of course, leads to this simpler equation. 1 equals a times 150 minus p plus b times p. Right, pretty simple. And now we can use this little equation to figure out what A and B are. Remember, that's our goal. We've got to figure out what A and B are. And so the trick is this: you take, you let P equal 150, and you plug that into that entire equation. And when you do that, you get 1 equals A times 150 minus 150, or 0, right, plus B times 150. And notice this term will disappear. That's 0. And so we end up with 1 equals B times 150, or B equals 1 over 150. Okay. In a similar way, if we carefully choose P again, and in this case let it be 0, we plug it in, we end up with 1 equals A times 150 minus 0 plus B times 0. We end up with A equals 1 over 150. Okay, pretty nice. Those become our values for A and B. So we end up needing to integrate, my original integral up here, right, let's write it down, was the integral of dP over P times 150 minus P. But now I've decomposed that into, I'll write it like this: 1 over 150 over P plus 1 over 150 over 150 minus P. Now, just so you know, I would normally write that I'd put the 150 down here, 1 over 150p, but just so we can keep things straight. And I can factor a 1 over 150 out of this entire integral. So I end up needing to integrate these two things. Right? That's this side right here, that right there. And I can integrate both of those. We end up with 150 out in front times, we end up with what? An ln of P. And again, we're assuming population is positive, so we're going to just drop the absolute values. Minus ln of 150 minus P. And that's the left side. That goes right here. And this right side is 0.0004 t plus c. And then we can proceed from there to figure out what p is. Okay. Of course, the way we do that is let's write down where we're at right now. So right now, this is where we're at, 1 over 150 ln of P minus ln of 150 minus P equals 0.0004 t. Okay, 0.004 t. Let's multiply both sides by 150. That's a plus c, right? Multiply both sides by 150. And that's going to give us 150 times 0.0004 is 600, or 0.06 t plus a different constant, 1/6 times 150, doesn't matter, we'll call it c. And then this side becomes ln of P over 150 minus P, right? Remember our rules of, that's not a 6, that is a c sub 1, right? We're just working through some algebra here. Exponentiate both sides. So this left-hand side is simply going to be P over 150 minus P. This right-hand side is going to be some constant times e to the 0.06 t. Okay, so now the question is, can we figure out can we solve that for p? And we can. I mean, there's a little algebra involved. You know, the thing we would do is we would multiply this over to that side like that, distribute it through. Let's move it this way since we're running out of paper here. So we distribute it through, we end up with P equals 150 C sub 2 e to the 0.06 t minus P C sub 2 e to the 0.06 t. Right? The reason we do that is because if we want to solve for P, we need to get all the P's on one side. So we move that P term over. And factor it out. And then we can divide by this term and end up with an expression for P. So if you go a little further in the book, you see that this is the solution to your logistic equation right up here. To this logistic equation, all right, with an initial condition of P sub 0 equals, or P of 0 equals P sub 0. Okay, let's just write this down. I think this is helpful. You can certainly derive this, but this will be the solution. M times P sub 0 over P sub 0 plus M minus P sub 0 e to the negative k mt. So that's helpful to know that that equation always has that solution, so that you don't have to go through the derivation of it every time.